Hello, this is Rasool Koosha, Graduate Research Assistant at Texas A&M University Turbomachinery Laboratory. This video explains how to use a pad model in Ansys to perform analysis with Excel transparent predictive tool. We use Ansys Mechanical APDL. In Ansys Mechanical APDL, first you need to define a new job. You define the type of analysis you want to have. It's going to be a structural analysis. And then you have to select the type of element. Make sure you always select a solid 8-point node element for the analysis. Next is the type of material you have. This is up to you based on the pad material you have. You should define the material properties. I'm assuming here that we have steel, so it's going to be 210 gigapascal for the elasticity and a Poisson ratio of 0.3. Next step is to generate the pad body. If you have a simple pad, you can simply generate it by the features that are included in the Ansys Mechanical APDL. If your pad geometry are rather complex, you always can model it in SolidWorks, CATIA, Ansys geometry, and then simply import it here using this tool here. For this case, I'm assuming that we are working with a simple pad, so I just use the features here to generate the volume I want. So I'm going to use the partial cylinder tool, and the geometry I am modeling here has an inner radius of 57 millimeters, an outer radius of twice, which is 114 millimeters, and an arc length of 50 degrees. And I assume the thickness is 20 millimeters. With that, I generate a pad geometry. You can rotate it. This section here is the pad top surface, and this section here is the pad back surface. The next step is to mesh this volume. First, you have to... Hello, this is Rasool Koosha, Graduate Research Assistant at Texas A&M University Turbomachinery Laboratory. Today is March 14th, 2019, and this video explains how to use a pad model in Ansys to perform analysis with Excel transparent predictive tool. To this end, we use Ansys Mechanical APDL. In APDL, the first step is to start a new job. Then we define the type of analysis we want to have. It's going to be a structural analysis. And in the preprocessor, we define the type of element we want to have. Make sure you always choose solid brick 8-node element. Next is the type of material. That really depends on the type of material your pad has. Here I'm assuming we are using steel, so it's gonna be 210 for elasticity and 0.3 for Poisson ratio. The next step is to generate the pad volume. If you have a simple pad, you can use the features in the modeling section to generate your pad body. If your pad body is rather complex, you always can model it in other softwares like SolidWorks, CATIA, or even Ansys geometry, and then import it here through IGES. Here I just modeled a simple pad geometry using a partial cylinder tool. I make a pad. I'm assuming that the pad inner radius is 57 millimeters and the pad outer radius is twice that, so 114 millimeters. The arc length for the pad is 50 degrees and the pad thickness is 20. Here is the pad. You can use these features to rotate it. This section here is the pad top surface facing the thrust collar. This section here is the pad back surface. Next step is to mesh the pad volume. We choose the type of material for this volume here. Since we already defined one material property and defined one type of element, it's going to be 1 and 1. So just press OK. Then we use mesh tool to define the number of nodes we want to have. So let's say we have 15 nodes along the radial direction. That means 14 elements. So I'm gonna put here 14. And then along the circumferential direction, I also want to have, let's say, 20 nodes. That makes it 19 elements. I add it here, and then along the pad thickness, I choose to have 5 elements, which is 6 nodes. After that, you just press hexagonal mapped and you generate your mesh. And okay. Now the body of the pad is meshed, so we can proceed to the next step, which is the solution part. However, before we do that, the Excel thrust bearing code or other analysis of the thrust bearing is based on a cylindrical coordinate system. So we have to change the coordinate system from the Cartesian, which is the default in the Ansys, to cylindrical. To this end, we change the active coordinate system to cylindrical. We align the work plane to the coordinate system, and then in the model we change the nodes to active coordinate system. Pick all, and that's it. Next step is to define the type of analysis we want to have. Since we only care about the pad top surface, the only nodes that matter for the analysis is the pad top surface, since those displacement of those nodes define the film thickness. So here I change the analysis type to substructuring to reduce the volume of the analysis we want to do. And then here it should be substructure analysis. Okay. Next step is to define the master degrees of freedom. As I mentioned earlier, the only degrees of freedom we care about or are important for us are the axial displacement of pad top surface. So here I only chose those nodes. Okay, and then here I only include the axial displacement. Press OK. So if you rotate it, you can see that only the axial displacement of pad top surface are selected. The next step is to define the boundary condition for the pad. That really depends on the type of pivot you have. If you have a spherical pivot, you should just define boundary condition for a few central nodes at the pad back surface, center of the pad back surface. If you have a cylindrical pivot or one-dimensional tilting, it's going to be a line of boundary condition. Here I assume we have a fixed geometry pad. That means all the nodes at the pad back surface are fixed. So I choose them, okay, and I set all of them to 0. So if you rotate it, you can see they are all fixed. The next step, I can just go and perform the analysis. If you see this sign here, that means the solution has been successful. So you need to get the data from the super element matrix. So you come here and you choose full content. Okay, so this is the file that we need to give to the Excel transferring tool so it can perform analysis. I for now save it on my desktop. Do remember, you should not change the name. Excel transferring is assumes that the name remains as SELIST. Just press save. That's it. Back to desktop, you copy this file and you take it to your Excel transferring base file. So for my case, my base file are in drive C, user, app data folder, local, temp, and Excel transferring, Excel TRC2. So you just paste it here. Okay, since a data file based on the pad model in Ansys is generated and is located in Excel TRC default folder, transferring predictive tool can use that model to generate elastic deformations. But before we do that, we need to make sure the pad geometry we modeled in Ansys actually matches the pad geometry we are inserting here. So the inner radius, outer radius, the pad arc length should match. In addition, the type of pivot we chose should be also the same. So I had a fixed geometry for my case. Let's say it's 80% tapered, and let's say it has 0.02 for taper angle. In addition, the pad thickness and the pad material properties should match too. So we should make sure the thickness is the same, the elasticity is the same, and everything. The other important parameter is the number of nodes we have. In the model I made in Ansys, I chose 15 nodes along the radial direction and 20 nodes along the circumferential direction, and 6 nodes in pad along the pad thickness. So since we matched all those, if we change it here from in-house finite element model to Ansys model, and we press run, we should be able to perform analysis using the Excel thrust bearing code. As you can see, the program is fast. Okay, so here are the results, and in the contour section you can see the film thickness for each case, the pressure field, and also the pressure deformation under this. So since we are using the Ansys model, we only can have pressure induced deformation, we cannot have temperature induced deformation. If you use the in-house finite element model, you will have both temperature induced and pressure induced deformation. In the 3D-dimensional plots, you can have the temperature distribution in the film, in the pad, and in the charts here you can have the power loss, minimum film thickness, temperature raise. As you can see, because we transfer to turbulent at this speed, the temperature drops. And that's it. This is Rasool Koosha. Today is March 14th, 2019.